my name is Rakeeb, and it's nice to meet you. I just, with this talk, I just wanted to go over concurrency as a whole and just get you guys curious. That's just a good way of saying that I'm confused about. So basically, let's start with the Wikipedia definition for concurrency. And since it's a lightning talk, let's just focus on. So basically, when I thought about concurrency first, I thought that it was parallel, or maybe it was something that was simultaneous. But it actually is supposed to be your code that can be executed out of order or in partial order. So that also inherently means that there's something to do with context there. And by context, I mean like I'm having a conversation with you guys. And whenever, so basically whenever you swap code out and you come in, you should carry that conversation on. So with that being said, let's go on to, you can't really talk about concurrency without a slide deck. So, so basically concurrency is something that the OS gives you, and basically the process is where the OS hosts your application, and it's basic space and time allocation. And you have threads there, which are like mini processes, which kind of chunk your code. I like to call them like units of work. So it kind of aligns with the definition of concurrency we just saw, with threads interleaving each other, which brings us to concurrency models. Can somebody guess what I'm trying to say here? Okay, so green threads and native threads. Okay, so with green threads, what the virtual machine or the runtime is doing is that it's staying in the middle. So whenever you spawn a new thread, let's say for example you spawn a new thread on Java, it's actually let's say you spawn like 20 threads, but the virtual machine is actually just playing around with 2 threads, so it's mapping. And with native threads, when you create a thread, you actually create a kernel level thread. So, okay, so there's a question for you guys, which kind of, anyways, is Java using current green threads? Anyone?
It used to.
Yeah, yeah. So yeah, it used to. Like it was back in 1997, I guess. So the main point here, it used to. And I did read up like for small embedded devices, it still does use green thread. So which we now come back to native OS threads, which Java actually does. And basically with OS threads, it's basically sharing stuff. And when you share stuff, it kind of gets messy. And you actually have to deal with mutexes, like mutual exclusions, where, for example, let's say I have a database access, and then I'm locking the access to the database when I'm working with it on different threads, like this mic. I'm using it right now, but I mean, you guys can't use it. So yeah, and then you also have a way to communicate back, like, hey, this mic is fake, which is also known as semaphores. So basically, when you're dealing with threads, the thread API, you're actually dealing with very low-level stuff. And then we kind of have some abstractions around that with thread pools, where you actually spawn an army of threads and kind of reuse them over time. So why this is a good idea is because, remember, we're spawning up native threads, which actually have a huge memory footprint, I guess. So again, further in the abstraction, Java has futures and promises. So this is actually linked to futures and completable futures, which has, so when you think back to the threads API, it's kind of straightforward. And it actually provides, the futures and promises actually provides a really good functional way to handle your concurrency. You actually don't have to deal with synchronization. And it's actually based on callback, so yeah, callback will be a thing there. And I really want to talk about non-blocking I/O. Also, in Java, there's this package called new I/O, which isn't apparently new, but it's like 12 years old, or maybe even more. So anyways, the thing with I/O is that it's the thing with I/O is that it's tricky because you're establishing a connection and then you're expecting some input, you're expecting some output. You can't like close it off. So with the new I/O, you can spawn a channel, like let's say a socket channel, or maybe a file channel, and then you create buffers, which are kind of the memory allocation you want to allocate. And then with the buffers and the channels, you have selectors, which can iterate through all those buffers through some event loop mechanisms. And then you also have pipes, which is used to communicate between different threads. And yeah, and that's non-blocking I/O for you. And for further study, I guess one can look at CSP, which is kind of what non-blocking I/O is doing. It's not exact, I would say. And you can also look at CPS, which like our friend just pointed out in Kotlin, what they're doing with coroutines is that they're creating this continuation stuff. Like when you think back to when I said about context, like whenever you're interleaving, there needs to be some context there. So yeah, that's CPS for you, and then you have also coroutines, fibers. So these are topics for further study. Like I said, I want to leave you like curious. So yeah. And also, I don't know about them so much. So. Anyways, that's all I have for you, and let's end it here.
Okay.